This is problem 3 on practice exam 1 in chapter 1 from the book Problem Solving Guide for Differential and Integral Calculus. We have simple harmonic motion. This is the general form of simple harmonic motion. X is a cosine omega t. Of course, it could be sine either. You can also have a phase angle in there. Not important. X is the position of the object. A is the amplitude of the motion, that's the angular frequency, and t is the time. Here is a map of position versus time given by this normal equation. Actually given by this specific equation, x is 5 centimeters cosine 180 degrees per second times the time. Carefully estimate the speed of the pendulum bob at 1.5 seconds, right here, by drawing a good tangent line. We want to draw a tangent line that approximates, that follows the curve at 1.5 seconds. Well, first we'll put a dot there, and we'll carefully draw a tangent line. Now we have to get the slope of that tangent line. The rise is easy. It's the whole span of the graph. Minus 6 centimeters to plus 6 centimeters, that's 12 centimeters. The run is from this time, somewhere up here, and this time, and the tick marks are down here, so let's draw some vertical lines. So this is 1.1, maybe that's 1.11. Let's drop a vertical line here from this, and then this is the run. This is the run, 1.58, 1.89, something like that. So the rise over the run, that's the speed at that point. 12 centimeter rise, 1.89 is this point, 1.11, that's 0.78. 12 divided by 0.78 is about 15.8 centimeters per second, and we should be happy with that. The actual speed's 15.7, so we're pretty close. That's a pretty good tangent line. Part B. The actual tangent line follows the line pretty closely at 1.5 seconds. So let's get the average speed from 1.5 seconds to 1.6 seconds and see how close it is. There's 1.5 seconds. There's 1.6 seconds. To get how far it goes, we can use the normal equation. We can get those two positions. This normal equation will give us the two positions, and we can subtract them to get the distance traveled. So here is our line that connects the 2 points, and you can see that it follows the actual line pretty closely. All right, there's the tangent line. It's actually curving over a little bit, so maybe our average speed is going to be less than here because it's slowing down. The average speed over this interval is going to be less than the speed here. Not by much. Okay, so let's check where it is at 1.5 seconds, and we can use the normal equation. We plug in t is equal to 1.5 seconds. There's our t, 1.5 seconds. Cosine of 180 times 1.5 is 270. Cosine of 270 is 0. 0 times 5 centimeters is 0, so we're not surprised at all that it's 0 because that's where it is. The equation gives 0. And we should expect this to be 1.5 or 6 or something like that. That's what it looks like. We just plug in 1.6 seconds and see what we get. So 1.6 times 180 is 288 degrees. We take the cosine of that, multiply by 5 centimeters, 1.5451. That's this point. So if it starts at 0, it goes up to 1.5451. It traveled 1.5451 centimeters. And it did it in 1/10 of a second, from 1.5 to 1.6. The slope between those 2 points, not the slope of the tangent line, they should be close, but the slope between those 2 points is 15.4. And the speed at 1.5 seconds is 1.57, and we're happy with that. So we use the normal equation to get the average speed between 1.5 and 1.6. Now we're going to go even closer. 1.5 to 1.501, 1,000th of a second after 1.5 seconds. I can't even put a dot on there. It's going to look like the same dot. Okay? So at 1.501 seconds, it moved 0.0157 centimeters, and we know it did it in 1,000th of a second. The slope is the rise over the run. These are 2 points that are very close together, around 1.5 seconds. So that's 15.7079, which is to 6 significant digits, the slope at 1.5 seconds. So the slope at 1.5 seconds and the slope between the 2 points, 1.5 and 1.501 seconds, is the same within 6 significant digits. And of course, we're not surprised. That's problem 3.